No. All right, so today we are talking about the equilibrium constant. So obviously this tells you about where the equilibrium is for a given reaction. It tells you if it's going to make more reactants or more products, basically. All right, so I'm going to write out a generic chemical equation, and then I'm going to show you what the equilibrium constant is. So let's just write this, and it'll make some sense in a minute. So a chemical equation might look like this. A plus B produces C plus D. And when we balance the equation, we would have little numbers in front of these. And so what I'm going to do is I'm going to put lowercase numbers to indicate the coefficients if it was balanced. So it'll be lowercase a, lowercase b, lowercase c, lowercase d. Now, Taiwan, shut the window. You can move up to here if you need to, if you're too hot. All right, so what I'm going to do, I'm going to write out what these are just in case you get confused, okay? So capital letters has two T's, right? Letters are the reactants and products. And really, since this is a reversible reaction, it doesn't matter which side we call reactants and which side we call products. But as a convention, we're just going to call the left side the reactants and the right side products, even though the reaction goes both directions. So these are our compounds or our elements. That's what the capital letters are. Lowercase letters are the coefficients. Something like that. There we go. So that's when you balance the equation, you put a 2 or a 3 or 4 next to something. That's what the lowercase a, b, c, d are. All right? So what is KEQ, or equilibrium constant? All right, well, it's represented by a K, right? Things are constant. We like to write a K because the word constant is spelled with a K, right? No, we use K anyway. I have no idea why. Sometimes we use C, but sometimes we use K. It's almost spelled like K. All right, so KEQ, the equilibrium constant, that's what it is equal to the concentration of the products, so that'd be capital C times capital D. So this would be the molarity of each one, right? The concentration of each one. So if it was, you get the idea. And then you raise it to the power of whatever the coefficients are. So if there's a 2 here, if there's 2 times this thing, then this will be squared, right? If it's 3, it's cubed, and so on. And then this is divided by the same thing for the reactants, these ones here. So it'll be A, concentration of A, to the power of whatever the coefficient is, times concentration of B. There we go.
So we're going to start going into numbers now?
Yes. And that'll just be today, and then tomorrow we'll start a practice test. So I'm only going to spend one day on this. What I want you to get from this, the big key idea here is this. Products are on top, or the right side of the equation, since it's reversible. We'll call them products. They're on top. And reactants are on the bottom, or the left side of the equation. So if I get a K that's a really small number, that means that the denominator is big and the numerator is small, right? If I get K less than 1, that means the denominator is bigger than the numerator, right? And if this is bigger than that, that means we're making more reactants. There's more of these and less of these. So if I make this reaction happen and I let it sit there for a while and it goes to equilibrium, and I find I got a whole bunch of these things and very little of this left over, these are all used up making that stuff, then that means the denominator is going to be small, really big. And that means it's going to be less than 1. Does that make sense? So if it's less than 1, we produce more of the stuff that's on the left side. Okay, so we'll say favors left side which also means reactants. And if K is greater than 1, then it favors right side, or the products.
So if it's less than 1, then A and B go up top?
No, if it's less than 1, it just means A and B are big and C and D are small. So that's what K tells us. And remember, it's a fraction, so that means our lower limit is 0, right? So if we had a reaction where all the stuff turned into A and B, and all of C was gone, C and D, there was nothing left, then we would end up with 0 for K. So that would be like a reaction that only goes one direction. Like if it was just like this, that would give us a K that's 0. And if on the other hand, all these got used up and all those were produced, right, then our upper limit, that would be infinity, because we would be dividing by 0, right? So, but it goes both ways. So if we end up with like 1,000 or 1,000,000, that means a lot of C and D are produced. If we end up with 0.001 or 0.0001, really tiny number, a lot of A and B are produced. That's how it works. So 1 is like the middle number. You either got a really big number or a really tiny decimal. All right, that's enough of me talking. Let's do a problem with this and then try and make some sense of it. I'll leave this stuff here and this stuff up top here, and then I'll do it down here. All right, so let's say, and I'm just going to give you the numbers here. So let's say we have a reaction, N2 plus H2, and this is, a real reaction. So nitrogen and hydrogen gases make ammonia. And if I were to balance this, there'd be a 2 in front of ammonia and a 3 in front of hydrogen, right? Make sure I didn't screw that up. So let's say we do this. We mix these things together. We mix some hydrogen and some nitrogen together. And they start producing some ammonia, and they reach equilibrium. And then we measure the concentration of each one. So the concentration for nitrogen gas, let's say, is 18 molar. And the concentration of hydrogen gas, say, is 13 molar. And the concentration of ammonia, NH3, is, let's say, 8 molar.
Okay, you just made those numbers up?
I just made those numbers up.
Okay.
And so what I want to know is, based on these numbers, and these numbers could change if you change the temperature of the system or the pressure, right? But based on these numbers, what is the equilibrium constant? What's K for this particular problem?
So this is going to be 18 over 2.
All right, hang on for 1 second. This side here is the product side. So this side goes on top. And there's only one product, so we're only going to have one thing. We're going to have a C. There won't be a D because there's only one thing over there. So it'll be whatever this is, concentration of ammonia. So it'll be 8 molar. You can throw the number out and just write the 8 in there. And then to what power?
2.
2 squared, right? And then on the bottom we have our two reactants. So it'll be 18. And that's to the 1 power, so we won't write it in there, times 13, and this is the hydrogen, so that's to the 3rd power. That should be a 3 there. It's meant to be a 3. There we go.
But for the top, what about the 3? Like,
Tell me, what are you saying?
like over there, so where?
This?
Yeah.
That's just part of the formula.
That doesn't have anything to do
Nope,
with.
doesn't change anything. All we care about is the amount of each one, the concentration, and then the coefficients that go next to them. All right, so let's plug these numbers in. Let's do top and bottom separately so we don't screw up the math. 8 squared is 64. That's not how you write 64. Bottom, we got 13 cubed. 13 squared is 169 times 13 is, I don't know what. Somebody do this.
Kind of.
Let's do a calculator. That works better, right?
39.
Say it.
3,197.
3,197?
2,000.
2,197. And then we're dividing? What do we get?
Wait, times 18? Wait.
Oh, times 18? Okay, do that too, yeah.
Okay. Oh, 39,546.
Make sure she didn't time. Yeah.
Got it, okay,
What did
yeah.
I do?
All right, so now 64 divided by that Should come out to at least 2 or 3 zeros, right?
0.001,
0, 0, 1, what's after that?
6, 1.
6, 1. There we go. So a tiny number. And look, what does this tell us? K is less than 1, so that means it favors the left side, right? There's a lot more of the things on this side produced than there is the things on this side. That's how this K thingy works. So there's our answer. Questions?
Oh, how's that 8?
It's from this here. Concentration of ammonia.
Can you do another one?
Where'd you get the exponents from, though?
The exponents are this number, and the 1 that's there.
But it's not really there.
But it's not really there. But it is there, I just didn't write it.
Okay, okay.
If we put a 0 here, that'd become a 1. Right? All right, do another one.